All right, sorry, let's try that again. Okay, so here we go. Here's number 16. So we got the canoe. Roy's at the left end. Sally's at the right end. The canoe itself can be treated as a point particle located at its exact center. Okay? And then I will always use an X to mark the center of mass of the system. So I don't know exactly where the center of mass of the system is, but I can probably give a pretty good approximation. Is it going to be more to the left or more to the right? More to the left, because Roy is bigger than Sally, right? So this X is going to represent the center of mass of the canoe. Okay? So here are the other things I know. I know that Roy has a mass of 80 kilograms. I know that the canoe itself is 30 kilograms. I don't know Sally's mass, so I'm going to use MS for that. Good? All right, so that's our setup. The only other thing we know is we know that they're sitting 3 meters apart and that they're sort of evenly spaced from the center of the canoe. Good? So what that means then is that this distance here is 3 meters and that this distance here is 1.5 meters. Follow? Any problems? All right, so then what happens is they get up and they switch positions. Okay? So let's think about what's going to happen. So in order for Roy to go to the other end, he's going to have to walk, right? So action, reaction. How does Roy walk to that end of the canoe? Static friction, right? So the action is Roy pushes canoe backwards, canoe pushes him forward, right? So that he can walk the 3 meters to the other side of the canoe, right? Okay? And then Sally does the same thing. She moves to the other end. Who is it going to take more force, and this is a little bit sloppy, but who's it going to take more force to move? Roy, because he has more mass, right? Okay? So if you had to guess, during this exchange, do you guys agree that the canoe is going to move because they're both pushing the canoe? Which way do you think the canoe is going to move? To the left or the right? To the left, right? Okay, if that's not obvious to you, I'll show you another explanation for why that's true in just a second. Okay? Now, well, in fact, let's do that right now. So here's the other explanation for why that's true. All right, so this is, everything that's drawn in black is for before they switch, right? Okay, so let me draw the canoe again after they switch positions. So here's the canoe. Here's the canoe. After they switch positions, Roy is going to be over here, and now Sally's over here, right? Now where's my center of mass going to be? More to the right or more to the left? More to the right. So now here's my new center of mass. All right, now, what forces act on the canoe? There are, I would count, 4 forces acting on the canoe. So what do we got? Gravity, pulling it down. The buoyant force, the normal force, whatever. Technically it's buoyant force, but it's like a normal force. The thing holding it up, the water, right? Roy pushing one way, Sally pushing the other way, right? Are those internal or external forces? So if you're just looking at the canoe, those are external forces. And I'm wishing now I'd rephrased my question. Okay, so let's look at, because this X represents the center of mass of the Roy-Sally canoe system, right? So I should have looked at the Roy-Sally canoe system. So Sally pushing the canoe and the canoe pushing Sally, those are internal forces, right? Right. Similarly, Roy pushing the canoe and the canoe pushing Roy are internal forces, right? Okay, and then there's gravity and normal force that cancel. So are there any external forces for the Roy-Sally canoe system? No. No. So what's the net force on the Roy-Sally canoe system? 0. So what should be true about the acceleration of the center of mass? It should be 0. In other words, in English, the center of mass of the canoe shouldn't move, right? Make sense? So the problem references a post, like a docking post or whatever in the water. It doesn't tell you where it is. It doesn't matter. So let's put the docking post, I don't know, how about, I'm going to put it here. So there's my docking post, okay? All right, so then they switch positions. When they switch positions, the center of mass has to remain stationary relative to that docking post. So let's see, I need my center of mass to stay in the same position. Which way did the boat move? To the left. Does that make sense? So in other words, whatever this distance is has to remain constant. Yeah.
How do we know the net force is 0?
How do we know the net force is 0? Because all of the forces were internal forces. Does that make sense? Is that enough of an answer?
No, that's good.
Everybody good, you guys?
Yeah.
Any questions? I don't know why I'm wiggling my fingers like this. Stop doing it. It's a little creepy. Okay. So now we need to solve this thing. So to solve it, we need to develop a number line. Okay. So I am going to call the post 0, and then I'm just going to number this way. And for simplicity, I'm just going to make this way positive. Why did I do that? Because I'm dumb. Good? All right. So let me smallify this so that we have a little bit more room to work. It's the opposite of a big one. Okay, so the center, the position, the canoe, Roy, Sally's system, the center of mass of the Roy, Canoe, Sally system can't move. So let's write an expression for the center of mass of the system here. So let's see, it's going to be the mass of Roy, which is 80, times the position of Roy, which is 3, right? Plus the mass of the canoe, which is 30, times the position of the canoe, which is 1.5, plus the mass of Sally times her position, which is 0, right? Because she's at the end of the canoe, down by the post. All divided by the total mass, which is 80 plus 30 plus the mass of Sally. So that's before they switch positions. Peter.
So we're treating every single object in the system as if it were on a singular horizontal plane?
That is correct.
Okay. I think that's what messed me up, because I was like, conceptually, it's like, but they're on different levels, like vertically, and I could, my brain was going to
Gotcha. I would have to read. Can I steal this for a minute? Thank you. Yeah, I mean all of the values that are given to you are horizontal.
Right.
So yeah, vertically things get a little more complicated. So.
Right.
All right. So is everybody good with that? All right. So this is all before they exchange positions. All right. Now, it tells you that after they exchange positions, the canoe has moved 40 centimeters, so 0.4 meters. Does that make sense? So after they switch positions, let's do the same thing. So let's see. I'm going to do the same thing. I'm going to start it this way and work over. So let's see. The mass of Sally we don't know. Her position is now 0.4 plus 3 meters of canoe. So 3.4. Plus the mass of the canoe is 30 times what's its new position now, you guys? 1.9, right? Because it was at 1.5 and it scooted this way. So now we're at 1.9 plus Roy, and his position is
4.4.
how far is Roy from the? It's just 0.4, right? All over our total mass of 80 plus 30 plus the mass of Sally. Does that make sense? All right. The bottoms of the two fractions are the same, so they cancel out. So just set the numerators equal to each other and solve for Sally's mass. And you get 57.6. So,
what are these two? So the black and the red, those are the center of mass?
it's the position of the center of mass. Before they switch positions is the black, and after they switch positions is the red.
And it's the same position?
And it's the same position because
Internal forces, no external.
no external forces. It's the exact same reason that you and Evan met at the middle every time you did it. Follow, you guys?
Yep.
Questions? All right, there's nothing magic about the fact that I chose this point to be my position of 0. You know what I mean? Like, I could have picked the other end of the canoe to be a position of 0 and it would still work. Okay? It's arbitrary. You'd always get the same, well, assuming you did all math right, you'd always get the same answer for Sally's math. Good?
Yes.
Questions? Cool. All right. Yes.